Bless you. I almost don't want to praise this. Bless you. Okay, this is from the expected value section. Multiple choice exam is 4 possible answers. 4 choices. Say it that way. For each question, for each correct answer, you awarded 5 points. For each incorrect answer, 2. All right, so let's see. Correct answer, 5 points. Correct. Plus 5. Incorrect is 2. Off. And for left blank, you get no points added or subtracted. Okay, so if you don't know the correct answer to a particular question, is it your advantage to guess? So for one question, so can you set this up? So it would help me out a lot, and it would help you out a lot if you can set it up like this. List all the outcomes. And next to this, you could put in English, correct, incorrect, blank, right? So those are the 3 possible things, right? If you put something, you're right or wrong, or if you don't put something, then it's blank. That's all the possible outcomes. You with me? For a single question. Are you guys with me? What's up? You guys all right? Maybe something. Yeah, like we're in the same room with you. If you wanted more than that, too bad. All right, I'll just stick with it. If it's correct, what's my actual value for that?
Plus
5. Incorrect, minus 2. Blank, you get nothing. Taken away or given to you. So, 4 possible answers, and there's only one right answer, right? Blah, blah, blah. Blah, blah, blah. Oh, if you don't know the correct answer to a particular question, is it to your advantage to guess? So, what is the probability that I would get the right answer?
1
out of 4. And what's the probability that I would get the wrong answer then?
3 out of 4.
3 out of 4. Now this blank thing is not really a probability. It's part of the question. Should I leave it blank or should I actually try to answer? So if I leave it blank, I get 0. So now I'm trying to say if I do try to answer it, what will I get? All right, so this isn't really part of this. There's no probability associated with leaving it blank. You either leave it blank or you don't. You guys kind of with me here? Mm-hmm. We won't get into that. Okay. So then what do I do now with these values here? What do I do? Multiply, exactly, right? I multiply the value by the weight. So what do you get here?
1.25.
5 fourths. Blank. What do you get there?
Negative 6.
Negative 6 fourths. And then how do you get the expected value? You just do what?
You add them together.
You add them together, right? You multiply all the possible outcomes times each of their probabilities, and then you add those together. In fact, we developed that formula, all of us together. We actually came up with that formula. So what do you get when you add these together? Is that good or bad for you? Bad. It means on average, if I took this test 80 times and I did this, I would expect overall to lose how many points for doing that? You can do it. For each question, now let me see. If I take this as a one question test. If I do this for 80 of these kind of questions, if I do it for 80 of these kind of questions, if I always guess when I have no idea, I can expect to lose 1/4 of those, which 1/4 of 80 is 20. I can expect to lose 20 points. For every question, I'll lose 1/4 of a point on average. For a single question, does that make sense? Can you lose 1/4 of a point? No. But I can look at it over the long run. Probabilities don't mean a damn thing for one situation most of the time. You have to look at it over the long run. So that's bad. Is it good or bad? I gave it away. It's bad, obviously. You have a negative expected value for doing this. Now, if you can eliminate one possibility, that's the second thing here, right? If you know one answer is totally wrong, you just leave me out one, this is totally stupid. You can eliminate it, which means if you can eliminate, what does that mean? What changes?
The Probabilities.
You eliminate one possibility, right? So now what is everything based on?
Thirds.
Yeah, everything's based on, now you have three choices. So you can set up the same thing. What would it be here now? It's probably get it right.
1/3.
1 out of 3. It's probably get it wrong.
2
2 out of 3. Now see if anything changed. See if that made it better. See if it's better to guess or not. So I don't know if you've ever taken like a test taking course, or they have like SAT prep courses where they do stuff about multiple choice questions and specifically, and they say this is a thing. If you're going to eliminate a option, then it's better to go ahead and try to take a stab at it, depending on how they grade the test. I don't know if you guys heard. Some of you guys have done that. If not, just imagine it happening and you go, all right. Okay. Okay. Anything else from homework? Yeah.
Which one? 12.6, number 13.
Oh, okay, so let's get into that. Hold on to that. I want to actually give you the formula first. This is the one time the formula works better, is when I have nothing to count. They just gave me probabilities. I have nothing to count, right? Then the formulas come right in.
Okay.
All right. So anything else before we get back into this?
12, 6, 16. Sorry.
Just weren't fast enough. Yeah, same thing. It's the same section, so it's going to be the same idea.
12, 4, 24, and after, pretty much. Especially.
I like that. I like that. You're like, it's only one question, Joe.
Yeah.
All right, so if you can set them up like this, you're golden, right? Now, if you could set up a situation like this, so for 24, for example, 24, sorry, good.
I did set them up that way. I just wasn't sure if I had. I just wasn't sure. Like the answer I got seemed.
What'd you get?
Negative 49,994.93.
Yeah, it's no good.
Yeah, I didn't think.
Holy crap.
Yeah.
Who would play that? You'd have to be. All right, sorry. So let's see if we can set up number 24, and then the rest of them are set up the same kind of way, right? So 24 says 10,000 raffle tickets are sold for $5 each, right? So the tickets cost $5. So all your money that you could get, you must automatically reduce each by $5, right? You're out $5 to begin with. One prize for so 10,000 raffle tickets. 10,000 raffle tickets. One prize for $5,000. There's one for $2,500, and there's two for $1,000. You know, because 1,000. Assume blah blah blah. Oh, come on, really? Give me a break. Why did they give you that? All right, sorry. All right, so they give you more information than they should. I'm not going to give you all that information. You should be able to figure out the probabilities here. But it's probably I get $5,000. 1 out of 10,000 is only one. They actually tell you that. That's great. It's like, book, don't insult my intelligence as a student. You should say that to the book. And then you should stop talking to books properly. Especially if they're talking back to you and telling you to do things. So what's the situations? What could happen?
1 for 5,000.
Yeah, I could win $5,000. I could win $2,500. Let me put it over here because we got to adjust these a little bit. Like I said, I can win 5,000. I can win 2,500. I can win 1,000, or I could win nothing. So why did I move it over a little bit? Because how much do I actually get then overall? $49.95, $24.95, $9.95, and -5. So its probability of each one of these, like you said, it's 1 out of 10,000, 1 out of 10,000. For this one, what would it be?
2 out of 10,000.
2 out of 10,000. And then this would be what?
9,900.
9,996 out of 10,000. Oh, they make sure that you got a lot of ways to lose, right? Okay. All right. So is that? So that's the way to set it up. That's how most of those kind of work. Do you guys get the feel for this? You understand what's going on? So now everything should work out beautifully. So I'll get 49.95 out of 10,000, 24.95 out of 10,000. What you got, Jeff? 19.90 out of 10,000. Sorry. And then whatever. Let's see. 1,000 negative 49.80. Is that right? No. 49. Is that right? I could use some help. You guys get calculators in math class? Anybody got a calculator? Minus 30, so that should be
You're right.
49. Is that 80 or 70?
80.
80? Oh yeah, 80. Thank you. I should not doubt myself. Cool. And then you add all those up and you get the expected value. Oh, I see. So you just forgot to divide by 10,000, I think. The number you said sounds like... Okay. I didn't know what to expect, but yeah, you just didn't divide by 10,000. Should be... You should get... I'll just tell you. You should get a loss of $4.05. So if everybody who plays is losing $4.05, who's making that money? Where's that money going? Huh? The raffle people, right? It's raffle people. All right, maybe. So they have, whenever you have a raffle, you hope you got somebody sitting down and making sure that you're actually going to make money off your raffle. So that's how you set ticket prices, is you guesstimate how many you're going to sell based off of what prizes you're going to give away. And very often the prizes are set by how many tickets are sold in these small raffles. All right. Anything else from homework? Okay, all right. You guys look like I feel I'm ready for another break, man. Thanksgiving is going to be awesome. No, yes, hopefully yours will be okay. All right.
I'm gonna get
What's up?
fat.
Yeah, wear your old pants. You know, let it out. Yes. All right. So let's get back into section 12.6. So just to firm up a few things, so remind me, remember we did this, probably of getting a jack or a club. We did, I think we did almost exactly that question. There's something to be careful about with this. How many jacks are there in a deck of cards?
4.
4. How many clubs are there?
13.
But if you do this while you're wrong, yeah, because you've actually added a card twice, right? There's 4 jacks. Well, one of those jacks is a club. So you got to subtract anything that's both, right? Let me stop there. You guys with me? Does that make sense? So, or... Did I already tell you guys about the nice bouncer and the evil bouncer?
Yeah.
Or is like the nice bouncer. There's always going to be a bigger number because or says you can be this or this. And since the probability is top, since the numerator of a probability is the number of things that match what I'm looking for, I'm now looking for more things. Jacks or clubs. But there's not 17 things that individually match that. There are 16 things that match that, with one of those things matching both. Does that make sense? All right, maybe. Cool. So this will be 16 out of 52, which reduces to 4 out of 15. Cool. And then you can make that a percentage if you want to, a decimal, whatever. Okay, cool. I like it. So what about if I said what's probably I get a king or a red card? So how many kings are there? 4 kings. How many red cards are there? Half the deck is red, right? 26, but what have we done?
Added 2 red kings.
Holy shit. So we gotta subtract it off. Let it be that easy. Math is not always inexplicable. It's like, oh, we counted 2 twice, we better take them off. Right? So subtract the 2 you counted twice. So I want to make a formula out of this. Or whatever the hell. That would be 7 out of 13, or whatever that is. I don't know my division by 13s. So the formula, probability of A or B. It's the probability of A. See, what's 4 out of 52? That would be the probability of a jack. What's 13 out of 52? That's the probability of a club. Right, because there's 13 clubs out of 52 cards. And what's 1 out of 52? What's that? That's the one card that is a jack. And there's the word. I like it cool. I like it when it just happens. So I got to take or is basically add. Or is basically add. That's why I call or the nice bouncer. The nice bouncer in front of a club, you can have a lot of people in that club if it's a good card. Right? You with me? The mean bouncer, the and, always makes it less and less and less. Look at that number. That number is damn small. There's only one card that is jack and clubs. So and is always very restrictive. I know I taught you about the big scholarship book they used to go look at, right? Mm-hmm. And, you know, and, well, shit. So it's probably an A plus probably a B minus the probability of A and B. I got evil there. So there you go. There's the official or formula. Do you have to use it? No. If I give you a situation where you can count, you could have been smart. You could have said 4 jacks and then 12 clubs I haven't counted yet. That's 16. Right? You don't have to use a formula. Right, cool. So let's do this. Let me remind you about this. Who remembers how this works? What's the probability I get a jack given it's a face card? So what does that given do? If I give you information, what happens? Why is that a 52? Yeah, because what could have happened? Any of the cards, 52 cards, right? But now I'm giving you that it's a face card. Now how many things could happen? How many face cards are there?
Are you counting the ace as a face card?
No, there's no face on the ace. I know it rhymes. It's not good enough. So which cards have a face on them?
12. Jacks, queens,
Jacks, queens, and kings. I like it. Right? If you see faces on other ones, I don't know. So there's 3 for every suit, and there's 4 suits. There's 12 face cards. Are you guys with me so far? So don't worry. I know some of you guys don't know cards all that well. If I did give you a card problem, I'd have images of a deck of cards for you, but most likely I'd just not give you a card problem. Just beautiful for probability stuff. So how many things could happen here then?
12.
Yeah. So I'm telling you it's a face card, but I want to know the probability it's a jack, given that I know it's a face card. So out of 12 cards, because that's the face card happened. So it can only be 12 cards. Out of those 12 cards, how many are jacks? 4. So what's that become? 1/3. 33.33%, right? And what's the probability of a jack by itself? Let's probably just get a jack. What's the probability of a jack? 4 out of 52. So many out. What's that become? As a fraction.
1 out of 13.
I'm sorry. As a decimal.
0.076.
Good. All right. It's like 7.6%. Now, so tell me, did telling you that it's a face card change the probability it was a jack? Let me say this again. This is huge, and this is also really simple. So try to see. This is really simple. There's no trick to this. The probability I get a jack just by itself is 7.6%. So if I had money on the fact that the card I have is a jack, I'm not feeling all that good, right? It's like the doctor telling me I got a 7.6% chance of surviving. I'm like, okay, doc, I don't feel so good about that. But now if I say, given that you don't smoke or something, there's a greater chance you're going to survive. Given that it's a face card, what's the probability it's a jack now? 33%. I feel better. There's a better shot. I got a 1 out of 3 chance. So did knowing that it was a face card affect the probability that it was a jack? Yes. So what I would say is I would call, oh shit, here's a definition. I would call jack and face card, those events, I would call these dependent events. Because the probability it's a jack depends on whether or not I know it's a face card. Right? So these are dependent on each other. How are you guys doing? Does that make sense? Because, and how can I tell? What told me that? The probability that it's a jack changed once I knew it was a face card. So knowing it's a face card changes the probability it's a jack. So they're dependent. That makes too much sense. If you're dependent on somebody else, and they go somewhere, they do something, they lose their job, whatever, will that affect you? Yes. If you're not dependent, if you're independent from somebody else, independent, and they lose their job, that's not going to affect you. That might, you might not feel that good about them, but it's not going to affect you like that. Do you guys understand? So the word dependent and independent in probability means exactly the same thing we want it to mean, what it means in real life. So let me formalize this a little bit. You do that, John. You ready? If the probability of A given B, I don't know if I've given you this symbol. This just means given. The probability A given B. If that's the same thing as the probability of A. So B happens. Given that B happened, given it was a face card, given that you don't smoke, whatever, and A doesn't give a shit. Did A change? No. A given B is the same as what A used to be. Those would be independent. Blech. Independent. Does that make sense? One happens and the other one doesn't care. I would call those independent from each other. They don't care. So what's a physical example of that? Well, what's the probability of a jack again? Well, that was 7.6%, right? What's the probability of a jack given it's a club? What goes on the bottom now, given that it's a club? 13. Out of those 13 clubs, how many are jacks? 1, not 4, right? Because the minute I said it had to be a club, how many jacks did I throw away? The 3 that weren't clubs. So out of those 13 cards, one of them is a jack. And of course, 1 out of the 13 is exactly where that came from, isn't it? That's going to be 7.6% again. So our jack and clubs, are those independent or dependent? Did the probability of jack change given that it was a club? Did it? Well, what it used to be? 7.6. What is it now? 7.6. So did it change? No. So what do you hope we would call that? If something happens and the other one doesn't care, I would hope we would call it independent. And thank God math says this one time I'll make it make sense. Yes, independent. So the probability changes. If you look at the given and the probability actually changes, they're dependent because if one happens, it affects the other one. So for example, I see somebody walking towards me in the distance. It's too far away. I'm like, is that a woman or a man? Got a 50-50 shot, right? I don't know, I can't see. But if I saw that they got off a Harley Davidson motorcycle. Now watch, let me see if anybody gets upset about this. I'm not saying a damn thing about no women ride motorcycles. But what's the probability that's a man? Did it change? Yes, it went up. I didn't say it's definitely a man. I said the probability it's a man shot up, didn't it? Oh, they just got off a Harley. It's probably a dude. Right? You guys kind of with, is that person, is something wrong with the way they look at the world? No, they're a realist, right? Could be a woman, but it's most likely not. Okay, maybe. One semester I had somebody come up to me after class. What are you doing? All right, obviously you need to keep taking this class. Maybe it'll make sense. All right, maybe. So I would say that Harley Davidson motorcycle riding and gender are, or sex, are dependent on each other. Right? The probabilities change. I like it. Cool. I like it. So let's develop a formula for the given. Let's really analyze what we just did. What was on the bottom here and why? We put 13 on the bottom. Why? 13 cards that are clubs. So the given goes on the bottom, right? And we put 1 on the top. Why did we put 1? There's 4 jacks. Good, I like it. So let me show you visually. Although we kind of looked at these back, section 3.6 a little bit. We call them Euler diagrams, but the more general thing is Venn diagrams. I don't know if you guys have ever seen this too much. So here's jacks, here's clubs. Who's in there?
The jack.
Jack club. So if I told you, given that a club happened, one of these things happened, the only way that it could also be a jack is if it's in here. So what is this region in general called? So if I have A and B, what is this region? What symbol would you use for that region? Or what would you call that region? That is, I like it, but no. A and B. The things that are in there are both A and B. So what's in here? The jack of clubs. Why? Because it's both a jack and a club, right? If I had men and Democrats, who are these? Become a D, Jeff. There it is. Who are these people? The male Democrats. They're people that are both, of course, right? So this would be M and D. I like it. So what is the point I'm trying to make? The point I'm trying to make is, in general, the probability of A given B, and I might write it as, now you're going to run out of room, Jeff. A given B. Let me see if you guys can handle this. Maybe. No, you got to be careful. So there's 2 ways. I'm going to just write it the way you should. All right, I'm going to let you absorb that. Because real quick, what is the probability of jack and a club? 1 out of 52, right? And what's the probability of club? 13 out of 52. What do the over 52s do? Cancel. 1 out of 13 there. That's why that's why you can put probabilities on the top and the bottom. Maybe. So something interesting about probabilities, the formula actually never changes. I know I just wrote a bunch of formulas up here, but the formula for probability is always the total number of things that could have happened. So if I give you information, less things could have happened, right? If I said somebody on the earth did this thing, then it's going to be over, what is it now, 7, 8 billion people? 7 billion? You with me? But given that they are from Mongolia, I don't know. First thing to bring. Isn't the bottom going to get a lot smaller now? There's not 8 billion people in Mongolia. Thankfully, you might have to carry each other on your shoulders. I don't know the surface area of Mongolia, but it sounds like a cool problem to do. Sorry. So that, all right. So there's another formula. Hopefully you're collecting all these. Obviously on, our test is on, you got this Wednesday off. Our test is on the 2nd. If I remember correctly, so a week. So Monday is going to be our review day. Right? I don't know if you guys realize how quickly things are happening here. It's crazy. Once Thanksgiving is in our sights, the semester's almost basically over. Right? So we're there. We'll go over a formula sheet to make sure you guys got all the formulas you need. So finally, we can do this. What are we missing? We got a formula for or. We got a formula for given. We're missing a big one. And the funny thing about and, can somebody help me out with the algebra to figure out a formula for and? We already talked about this. I don't know if you remember it. I did my stupid cheap slapping thing, right? Yes? Are you telling me you disagree with me? It was stupid? It was stupid, but hopefully it sticks in your head. How do I solve for probability A and B to make its own formula?
Probability of A times probability of B.
No. How do I solve? I know the book says that. I hate the way the book writes it. It'd be probability of B times probability of A given B. Or probability of A times the probability of B given A. Either way. And we've already done this formula. I just didn't show you that this was the formula. So very often, I've given us a lot of situations where I could count what was going on. So I didn't need the formulas. I could just count what was going on. So let me remind you guys, I can't remember the exact situation we're in, but if I pick 2 cards from a deck of cards, remember that we talked about with and without, so let's do it without replacement. So if I do it without replacement, take 2 cards from a deck of cards. So I take the first one, feed it to my little brother. He's got a strong stomach. He does actually. 2 cards without replacement. Most probably I picked king and then 2. Bless you. Bless you. Good. So the first card, the probability of getting a king would be 4 out of 52 because nothing's happened yet on the first card. I've got all the cards in the deck, so it's just a 4 out of 52 chance. Times. Beautiful. What's probably the next card is a 2, given that I already picked a king. Well, how many cards are there now? 51. And out of those 51, how many are 2s? 4. So that'd be whatever the hell that is. So we did a series of problems like that. I just didn't tell you what the formula was because I wanted you to realize the idea is bigger than the formula. Formulas are almost always lacking. They're almost always because they're trying to show you everything that could happen when the idea is actually much cleaner. Believe it or not, I don't know if you ever heard a math teacher say that or ever thought you would, but that is the reality very often, is that ideas are a lot cleaner than formulas ever can hope to be. And whatever the hell that is, I have no idea. 1 out of 221? It's like, I don't know. I've given up. It's too much for me. Nobody else is helping me, so I'm just going to move on. It's like 0.04 something. I don't know. No, nobody's doing it. Okay. What do you get? 0060. Okay. All right. So 12.6 is all about or and. And just to point this out, on page 720, they have this formula here. Well, what's the only time this is true? What does this imply? What's this imply about this? Yeah, I like it. Okay, who said that? What'd you say? Okay, that's one situation where it could be true. When is this? See, that's the real formula. But when is this equal to this? When A and B are independent. I love it. So they kind of say in the write-up, assuming the other ones happened. Oh, that's horrible. That's the one place in this book that I don't like what they do. This is only if A and B are independent. That's the one time you just multiply the two together. Did we just multiply the probability of king times the probability of 2 here? No, we didn't. Is that the probability of getting a 2? No, it's not, is it? The probability of getting a 2 is 4 out of 52, isn't it? So where the hell that should come from? What was past us thinking? Past us. We were realizing that, given that we picked a king already, that affects the probability of 2. That's what this means. That's not the probability of B. That's the probability of a 2, given that I got a king already. That's why this is the real formula for it. It's only that if A doesn't affect B. That's the only way it can still be just B in there. Maybe. Guys look excited. Okay, last little thing. And then we'll look at the practice test, I think, to see what's going to happen. The last definition I've left off is the easiest one, thankfully. When we do this here, if I have a deck of cards, pick a card, how do I do that probability? Is it an 8 or a 7? What would it be? Probably get an 8 or a 7. So how many?
8 out of 50.
Yeah, how many cards match what you're looking for? 4. Why didn't you have to subtract anything? What do I have to subtract normally for or? I got to subtract any cards that are both, or the cards that are both 8 and 7. If there are in your deck, I'm not playing with you, man. You're like, no. You have an 8 on one side, 7 on the other side. Screw you. Get away. Right? Some of you guys are like, what happened? So I would say that the event of 8 and the event of 7, getting a card from a deck of cards, that those are mutually exclusive. If you are one, you can't also be the other one. I love the term mutually. They both exclude each other, right? So these would be mutually exclusive. So there's a question in the homework where it says, if I pick one card, what's probably get a red and a black card? And I'm getting way too many people telling me that. So I'm sorry you had to say that loud because I'm going to tell you why it's not that. Or I'm going to ask you why is it not? Yeah, it's 0. Are there any cards that are red and black? Officially. Don't say, well, it's got some red on the collar. No, get away from me. The king is good. No, get away. It's either a red card or a black card, right? It can't be both. So this probability is 0. So for anything that's mutually exclusive, the probability A and B must be 0. If they mutually exclude each other, there's no way that you can be both. Right? I used to say, what's dogs and cats? And then somebody told me there's a cartoon from a while back there. They're freaking dog and cat. And I don't want to think about the biology of what's happening with that show. We won't. We'll stop there. If you don't know about it, just don't look it up. So then I started doing salamanders and rocks. Right? There's no freaking cartoon where it's salamander. It's nothing like that. So either you're a salamander or you're a rock. You can't be both. Right? You with me? There's no way. So that would be an example of a mutually exclusive set of events. Maybe. Don't tell me there's some new stupid-ass show out there. Rockamander. Rockapillar, that's right. In my stats class, I was using a caterpillar and a rock. So he said, what about a rockapillar? I was like, get out of here. Some old unknown B-52 song. It's a rockapillar. Alright, I think that's everything that they talk about. Cool. So let's do this. Let's look at the practice test real quick, just so you feel a little better about what I'm going to ask you. Everybody got a practice test? Alright, so number 4 is kind of a conceptual probability question. Should be able to handle that. Number 6 is the tree diagram kind of question, right? Let me see. Blah, blah, blah. There we go. Number 7, number 8, with replacement, or number 8 without replacement. Those kind of things. And then number 9 is that I told you, I'm going to have a problem where I give you the chart. I'm going to ask you a series of questions. So let's do this. Ooh, that's kind of mean. I didn't mean to do that. Oh, well, too bad for me, Jeff. Number 9, part E. Look at 9E. Are being male and not voting independent? How would you check that? You can't answer that question with a paragraph. You can't explain to me, well, being male won't really affect... No, you don't know until you analyze the data. That's the whole thing. So this is a sample of people. I don't know. And in general, in the United States, being male might affect the probability you vote. I don't know. I haven't seen any studies done on that, but I'm sure there is an effect. Right? Who votes more? How would you answer the question, then? What would you have to look at? For 9E. Male and not voting. How would you figure out if they're independent? What do you have to look at?
Probability is a male.
All right, you got to look at what probably man is. I like it.
Probability that it's unvoting male?
Nope.
Or just not voting?
Nope.
Voting.
Nope. No. So I really want this to make sense. The only way you can check to see if they're independent is to see if one has an effect on the other. If you look at them separately, it's not going to tell you a damn thing. So just because the probability of flipping a coin and getting a heads is the same probability as rolling a die and getting an odd number, doesn't mean they're somehow mystically connected, right? No. You guys kind of understand what I'm saying? So for some reason people check to see if these are equal to each other. That has nothing to do with anything. That would just be coincidence if they were. It doesn't mean shit if they weren't, right? What I need to see is how do they affect each other. So what's the only probability thing that I have that shows how they affect each other? What's the only thing I can do in probability that allows one of them to occur to see how it's going to affect the other one? Given. So if I check this, so look at this and male given not voting. So if this changes the probability of that, then they are obviously dependent. If knowing that they don't vote affects the probability that they're a man, that means they depend on each other. They affect each other. Does that make any kind of sense? So here's the, in general, to test A and B for independence. It's one of those words you're not sure when to stop. It's like banana. No, you're right, Jeff. You need one more. There it is. Yay. In general, to test A and B for independence, if the probability of A given B equals the probability of A, then A and B independent. If not, then they are dependent. And please, I just wish someday I could figure out how to say this so it just makes as much sense as it actually does. If B happens and A does not care, then they are obviously independent. This is the only way you can see if that's true. If B happens, what happened to A? Did its chances change? If they didn't change, they're independent. They don't care about each other. Let that make sense. If they did change, then they do care about each other. Oh, that's nice. So in part E, on number 9, you see how part D I actually ask? Oh, I did ask you the right things. Part B, I ask you that person, well, doesn't know. That's too bad for me. Part D, I ask you that person will not vote given that they are male. So to compare that to the probability that they won't vote, you can check it that way. So I can either check to see if male and male not voting, given not voting, are they the same? Or I can check to see if the other way around. Probability of not voting given male. Does that equal probability of not voting? So do this favor for me. Let's try this out. Number 9. Everybody's got the practice test. What's the probability that somebody doesn't vote? On number 9. Female, yes, no, don't know. Let me catch it, sorry. 20, 30, 50, 11, 15, 26, 3, 2, 5, 4, 47. Either way you look at it, it should add up to be 81. Okay, so we've done a problem like this before. So the probability that somebody won't vote, they're not going to vote. How many won't vote? Yes, probably not voting. It's 26 out of 81. What's the probability they won't vote given that they're men? Given that they're a dude? Well, let's catch up to you. So given that they're a dude, how many people could it be then? I know it's a man. So how many people could it be?
11 out of 34.
It can only be 34 people, right? I know it's a dude. Do you see that? So when it's a given, you can actually just cover everybody else up. That's your world now. Does that make sense? Given that it's a dude, forget everybody else then. I know it's a dude. I can throw out the possibility of anybody else. So out of those 34 total people, how many match what I'm looking for don't vote? or not voting. 11. So 11 out of 34. Now make those into percentages and see if they're equal to each other. Some guys realize they don't reduce to each other, so I already know it. But what's the numbers? What's the percentages? Well, this is like 32 point. Is it?
0.
Who is it?
0.
32.5? And then this one is almost the same. Holy shit. Who is it?
I think it's 0.5.
I don't know. I don't have a calculator, so
I just have
I'm relying on crowdsourcing.
It's just 32.
32?
32.1.
32.
Oh, I cannot. 32 point.
It says 32.0987.
0.3209. Is that right?
Yeah.
0.3209. Is that what you guys are getting?
Yes.
So that's 32.1%. Okay. And then 11 out of 34.
0.323.
Ooh, that's really close. Ooh, that's evil. That was evil. So the real world, I would actually say it's close enough. But for us, I'm going to make it a very strict. I'm going to make it very clear on the test. If they're dependent, I'm going to make them really different. If they're independent, I'm going to make them exactly the same. You with me? This one is kind of evil, but are they the same?
Basically.
Are they the same? So very technically, no. They're not the same. So no, they are dependent, not independent. In the real world, I say that's close enough. Right? So that's a little gray area. I don't think I meant to make it that close. So I would say officially, by the book, these are dependent. Why? Because the probability of not voting, did it change given that it was a male? Did it change at all? Yes, it did change. Very little. Right? So in the test, I'll make it go from 32 to 48 or something. Make it really clear. Or 32.09, 32.09, so you know it's exactly the same. I like it. I'm nice like that normally. Practice test, I decided not to be nice. Alright, cool. Anything else on this practice test look really freaky right now? One thing I don't think I've done, this is the last problem I'll do. Real quick, just to do some real quick. Let's put my bag of poker chips again, green. Let's say there's 7 green, 8 blue, and 11 red poker chips. And I picked 2 without replacement. What's probably, again, red, red. Red rana. Well, it's the probability the first one's the red. So the way I look at this, there's 2 things happening. There's one thing times another thing. I get a red and what does and mean? And means multiply. What does or mean basically? Or means add, right? A or B is A plus B minus the and. And means multiply. Or means add, basically, right? You might have to adjust a little bit by subtracting for the or changing the second dude for the and. Am I going to change the second dude? Without replacement, so is the second dude going to change the probability? Let's find out. So what's the probability? The first one's a red. 11 out of 26. And then I feed that to my little brother. He's getting full. How many chips then are left for the second one? And out of those 25, how many are red? 10. I lost a chip and I lost the red chip. So both of them go down, right? So earlier we did a problem where only the bottom changed. So if I did, and then, multiply out whatever that one is. If I did probability of blue and then green, what would that be? 8 blue out of 26. That's the probability of blue. And then a green. So how many chips are there now? How many green chips are there? Still 7. I didn't pick a green first. They're still all 7. So why did this number change? Because I picked the red one at first and fed it to my little brother, right? Green was 7 and then whatever the hell that is, blah, blah, blah. Alright, maybe. If you do the homework, you should be okay. So I'll have the answer key for the practice test on Monday. Do not come to my class on Wednesday. If you have other classes, you should probably go there. Sorry about that. I'm taking the day off.